Thank you. Thank you for that introduction. Thank you, everybody, for being here. Let me just see. So I'm now sharing my screen. So I'll start by doing a quick recap of what we've done, and maybe also a little bit of what we're doing, generally speaking. So Lawrence shared already in the chat there's a GitHub repository where I've put everything we've done, and actually including the output. But we have the data, which you can get from this link, and the data, what it looks like is a set of mags, or this is the output of something like semibin or whatever your favorite binner is. After you've processed your metagenomes, that would be a completely separate thing. But here we have a few of them. I think was and we did in the first session we ran CheckM2, which is basically the state of the art. It's a tool actually I was not involved in that tool, but Alex, the first author, he sits. I can almost see where he sits from here. And then last week, what we did was we then took the outputs of CheckM2, which is this big table, and we started to try to get some nice visualizations, and we ended up doing this plot here, which is plots completeness versus contamination, which are the two main metrics that we use for evaluating genomes. It's a completeness. All of these are estimates, so this is not ideally the true completeness is there's a genome that exists in our sample, and if we get every single base pair from that genome, we have 100% completeness. If we have some gaps, but the gaps are only 5% of the genome, then we have 95% completeness, and so on. And then on the other hand, contamination is how much do we have in our genome that actually does not belong to the original genome, right? And so what we want, an ideal genome is right there, 100% complete, 0% contamination. Again, we don't have the true values. What we have are estimates, and this is what tools like CheckM give us. So CheckM and CheckM2, internally they work very, very differently. Actually, it's a completely different way of estimating these, but they're trying to do the same thing. Is trying to do exactly the same thing, which is to try to get us these two numbers, and these are the main numbers that people look at. And generally speaking, we want something that's here, and there's a couple of standards for these, where if a genome is in this quadrant here, so generally 90% complete or more and below 5% contamination, we say it's a high quality mag. In some standards, high quality would also mean looking at a few other things, and we can talk about that today. But this is what we did last week. So we, this is just a standard scatter plot, and then a lot of the effort was trying to get these things to line up. These, right? And then I also mentioned that. So this is live coding. It's which is different from a tutorial. I also often do tutorials, but the biggest difference is that in a tutorial. So in a tutorial, what I do, and this is what everybody does. It's not cheating. It's what it is. So in a tutorial, I would have prepared all of the code, and then I'm just demonstrating. So in the tutorial, I'm saying, oh, this is what you do, and I would have before, and this is the preparation for a tutorial. I'd have before already planned out exactly, and maybe even during the tutorial, you're basically just copying and pasting from a pre-prepared solution where we know that everything's going to work. And here today, I'm doing a little bit more live coding, which means I know what I want to do, but I don't have the code. I don't know. So to some extent, part of this is also to demonstrate that there'll be some sort of all the normal coding stuff of, typos and functions that, how to, so with that, what do I want to do today? So we talked a bit at the end, there was someone who asked a question, and I apologize for forgetting their name. What else can, so completeness and contamination, probably the two metrics that are really the most, the most important, but there's a couple of other metrics that you also get from CheckM2. So we will look at those. We will try to do a little bit of plotting of them, and then maybe the last. So if this doesn't take too long, then maybe we can talk and hear just more a chat. I can just show a couple of other things that we could have done for quality control that we won't do, and then we can have a few minutes for questions if there is. All right, so let's go back to the code. So okay, so this is where we left off. Everything's on Git. Let's see. Oh, I'm gonna. Here, there it is. That, and so this was the quality figures. So this is what we did before, right? So in the end, it's actually surprisingly, we took a good 45 minutes to write these 23 lines of code. This is also not unsurprising. So let's start there. Let's do this. Let's start by loading. So let's start by repeating what we did last week. Oh, sorry, forgot to get the. So we import everything. So polars, seaborn, a matplotlib. Oh, sorry, I'm messing. I should be using the Pixie shell. So actually we started by installing Pixie, making sure that everything's there. Okay, this is what I want. And now, okay, we import polars, we import matplotlib, we import seaborn to make things nice. And now we read that in. Okay, this is what we did last time. Yeah, so this is what we did last time. Okay. And here, but the table has a few other things. Okay, so there's. So name. That's just the name of the file. Completeness contamination. This is what we were looking at. Completeness model used. So this is a very internal. So this is a very internal thing to. So I can use value counts just to see, that's apparently out of these 134 mags, 84 use the neural network model and 50 use the gradient boost model. So this is a thing internal to CheckM2. It's really not something that you as a user generally should be looking at too much. But it doesn't really, it's not really that informative except potentially for debugging. Counts. Okay, all of them use translation table 11. So this is the genomic code. So 11 is the standard bacterial translation table, and then there's a few weirdos that use translation table 4. And actually, we've been looking a little bit in the streams that I usually do. We've been looking at how these actually the organisms that use translation table 4, and these are things like MTB or mycoplasma. Generally speaking, they tend to be weird in many ways. Okay, so that's also. So, but 11 is the normal. Most organisms use 11, and so CheckM2 uses a a heuristic where it actually tries both 4 and 11, and then if 4 looks much better, then it uses, then that's what it uses. That's what it uses. But by default, it will pick 11, and that's the correct thing to do because that's what we think most organisms do. So coding density. Sorry, I'm going to move myself a little bit towards the center. Most better. But coding density. Yeah, this is basically how much of the genome is coding. We can use this here to describe function of this. Describe. There's just to have a look. Okay. All right. So we can see median is 87% or 88%, 55. I would potentially be interested in what is this outlier. So I think, or so let's see what it is. Oh, sorry. Sorry, that was a bit of pandaism. So yeah, so that was, so I just wrote pandas code, which is a different. Okay, so there's some organisms that have very low coding density. Not sure. So one of them has relatively low completeness. Sorry. Yeah, and not sure what that means. But so maybe we can. Let's just do a little plot. Let's just put the coding density. Let's just visualize. Okay, so this is what the coding density looks like. You can see it looks pretty good, but there's some outliers, and maybe we'd flag these outliers to have a little bit. So here in this plot, so I plotted the box plot and then plotted the dots. So the outliers got plotted twice, which, so this dot and that dot, this is the same thing. But the code, yeah, I would look a little bit at what's going on here. Maybe these are actually, this could be, yeah, so maybe some of these could be misassigned coding tables. But generally speaking, the data, this is what you'd expect. I mean, bacterial genomes are mostly protein coding rich. There's a few non-coding elements, and then very short, generally intergenic regions. This is very, very unlike eukaryotic genomes. But this is okay. So let's just actually I'm gonna skip contig and 50 because I want to come back to that a little bit. And I want to just look at average gene length. Maybe I want to do actually the same thing. Just to have a can. So this is pretty typical. So this is the size of genes in amino acids. This we've been looking at this a lot actually, and this is pretty typical, about 300-ish. This is something. Okay, let's actually do this. Let's do one versus the other. Oh. Okay, actually, I had not seen this. So we've been looking at this data for a long time. Actually, I had not seen this effect, but there's a few extreme organisms that have fairly extreme in both of these metrics. So this is actually the. So X is okay. Actually, this is not true. It's not. Okay, I'm gonna do this. I'm gonna multiply by 100. So I would probably now flag these ones here, these outliers, and maybe look at them a little bit closer. It could be that so as I said before, so CheckM2 basic, and this is not even CheckM2's original. I mean, this is something that other tools do. Uses this heuristic. Sorry, uses this heuristic to guess to estimate what coding table to use, and maybe it's getting it wrong. Actually, so maybe right. Okay, I was just exploring the data a bit, but maybe this last bit I want to save. So I'm going to move this to this code that I ran on the shell, and I just copied it to the file so that we save it. This was this was actually nice. Just run it again. Okay, and actually let's just let me just add the yeah, I did a micro change there. I think this is, I prefer it that it's just a style thing, but yeah. So okay, so this is not even what I wanted to get to. What I wanted to get to was were these contig and 50 genome size and total contigs. So so these are actually, so let's start here, total contigs. So this is the number of contigs in the. These are the total number of contigs in the mag. So these are mags from long read sequencing. So the contigs are long, including some of them, a full 25% are or more. Actually, we can actually check. We can actually just check the exact number. A full 26. A full 26% are single contig, meaning we have only one contig that is the full genome, or at least that's almost full genome. And then even the median size is only 6 contigs. Sorry, give me 1 second. And it. And so this is also an important metric for whether how good our data are. And then the other important metrics that I wanted to look at are the genome size is also very important. It's a little bit hard to read like this, so I'm just going to divide by 1,000,000. Right, bacterial genomes are, this is the right order of magnitude, 4.8, 3, 4.3, 4.7. This is right the standard. I think the standard E. coli is 4.6 megabase pairs. So in this size range, yeah, this is a reasonable-ish genome. So this is something, and then the other is the contig. Contig N50, which again maybe we wanna. So is this true? Oh, sorry. Oh, okay, yeah, makes sense. So the contig N50, this is a little bit. So this is the how big is the contig. So if you sort the contigs, so that you start with the longest, and you keep, and then you add the second longest and the third longest. Eventually, you get the full genome. But at some point, you will have half of your genome. And so you'll be at a certain contig in this order, and how big is that contig? And so you can see this is 475K. This is 1,000,000. So this is so these are pretty big. So it's kind of N50. It's kind of a median. It is a median in a sense, but it's not the median size. The size of the median contig, it's the contig that's in the median, if that makes sense. So this gives a decent idea of how big things are. Or I think the contig. So I think if you're a base pair in the genome, how big is the contig in which you're in, and what's the median? I think this is the way you get the N50. So this is pretty decent. This is actually very good. You don't get anything like this with short reads. With short reads, this would be a full order of magnitude smaller. So this would be 47,000 instead of. And now what I wanted to do, and this was actually my original plan for today, is to take the these total contigs and the contig length, and these are also very important metrics. But I wanted to take the total contigs, and I wanted to add it to this plot. So I said last week, this plot was pretty nice, but we were still missing. Everything was blue. So maybe we can add another. So here we have 2 dimensions. We can add a third dimension, which is using color. So we're gonna do that using. And I wanted to I wanted to use these metrics so that the config, the total number of contigs, probably a good one, or the config length, or the total length, probably good. So this is what I wanted to do. But then, so let's start with what we had. So this is what we had. Okay, this is what we had. And so here, so this, so we wanted to scatter, but add as a color. So as a color, we are going to add the config length. So, oh, sorry, the total number of contigs. So from matplotlib. So CM is the color maps. And then okay, oh, sorry, got this blocked. Yep. Oh. So this is okay. All right, we can choose a color map. So we want a sequential color map, I think. So 3D, this is good. But let's use or yellow, orange, brown. Or 3D this. Or let's. All right, let's use really this. Okay, how do I get this? So how do I add? So I think there's a color argument, but I'm not sure how do I pass. I think I pass it color. C, okay, it's C. Okay, how does this look like? Okay. So I need to. Okay, yeah, so this is. Okay, so this is what I wanted. Looks a bit weird. Okay, so let's. Okay. Yeah, let's okay. Okay, I'm doing again. So I've actually coded a lot doing this way. So I did it first on the command line, especially for this type of plotting code. It's and then so first you do it on the command line, and then you save the results, and then you edit it quickly. Mostly removing things, to be honest. Sorry. Okay, so this is what I. Okay, so we messed that up. Not sure why. Okay, all right, we messed that up too. Oh, I see. Okay, so color. Okay, this is okay. We messed that up big time. Yeah, okay, let's put it for no top button. Yeah, that probably looks. Okay, I like this. Oh, I see what's going on. Okay. Yeah. Okay. I see what yeah. But now this one is not aligned with that one. Then. I don't know what to do. Let's see what. See, I think we need to do this. Two. Okay. Not at all what I expected. Let's do this again. Okay. Okay, fine. That's where it belongs. That's where it belongs. That one goes away. That one goes away. That one's there. Fine. Everything's fine. Yep. Now this one messes everything up. Because of this. Yep, okay. Yeah, we want it to be vertical and not okay. Yeah, okay. Okay, this is what I wanted. Okay. All right, so yeah, so this is it. Maybe we could make it a tiny bit. Yeah, this is it. Okay, this is it. I mean, this is quite good. I mean, for a full publication quality, I would probably still fiddle with it. For example, I would probably want to flip the color bar around so that the smallest numbers are on the right, because in this case, the smaller the better. Maybe that's a bit. At least I would like to try it. But I think now, yeah, can we add a yeah, we can. Let's add a. Okay. Sorry, I messed this up. Sorry, I messed something up here. Yeah. Yeah. Oh, wait. Yeah, I think this is quite good. All right, so I'm gonna save this. Well, let's actually save. Or I'm gonna merge this into the main code. So we can remove this. So what change? Right, so here, oh, by the way, I didn't explain this one minor thing that I did. I'll explain it in a second. So there's a minor thing that I did, which is, so normally we just call these functions like, you know, like, from Matplotlib. Normally we just call these functions like scatter or, you know, like hisplot that create the plots, and then we, you know, we just call them. But in this case, I save the output, what the function returns, because I want to use it here for the color bar. So Matplotlib tries to do this by guessing. It works okay, but sometimes it guesses wrong. So there's really no harm in just being very, very, very explicit here. And now if we just do the quality figures, if this works, and so I am going to just going to add. Okay, we have a few minutes. Versus what did we have? Plot. Oh, sorry. Okay, and now I'm just going to push this to GitHub, and it should update there. Yeah. All right, so so we still have about 10 minutes, so I just wanted to very, very briefly discuss a couple of other things you could do with the genomes. So another tool that we have is called Chunk. I'll post. So this is now not stuff I'm going to do because we don't have the time. But I'm just going to talk a bit about it, about things you could do. So you know, this is a little bit of a self-promotion, but it's actually been quite successful, and people are using it. So this is a completely different concept than the one from CheckM, but so it provides some sort of, you know, orthogonal check that you could do. The other thing that you can do is you can, especially if you have long read metagenomics, is you can try to look for the ribosomal genes. So in particular, in the case of bacteria, that would be the 16S, the 5S, and the 23S. And there's a tool called BARNAP. There's a paper. And first, actually, should also post the paper. So, guys, I'm not actually finding it. A tool called BARNAP from Thorsten Zimmermann. So it's sort of a big Australian contribution to microbial genomics, Thorsten. And yeah, so whether that the genome has these ribosomal genes is part of the standard for calling it a high quality genome. It's almost impossible to get them with short read metagenomics. So it's actually not, with short read metagenomics, actually it's very, very rare that you get them. And I don't think you ever get them all. You do with long read metagenomics. So with short read metagenomics, in practice, most people ignore this criterion because it's just impossible to fulfill. It's not a reasonable expectation, but it is becomes a reasonable expectation with long reads. So you can run barnap. It's not too difficult to run, install, and then it will tell you, that in this your genome has 16S at these positions. It can also extract. You can also extract the actual sequences that, and for example, this is something I've been doing the last like yesterday I was doing this. You can then take your sequences and, for example, look at, and I was using this particular database where you can search your 16S from your mag, and then you can find, for example, we have that, one of our dog mags corresponds to this particular sequence, and it has been found elsewhere. So running barnap, or there's a couple of other tools, but I think barnap is the most widely used one. It's another way of doing quality control, and if you can find these 16S, 5S, 23S genes in your genome, that is also a mark of very, very high quality, and that is actually part of this standard called the NIMAC criteria, which, as I said, very, very rare to get them with short reads, but with long reads it becomes possible. And so that's also part of evaluating quality. Also gives you other possibilities that you can then link your mag to all of these 16S databases. All right, so we have about 7 minutes. So I think I can maybe give it over to anybody who wants to ask questions, or we can just wrap up a bit earlier. We have, I pushed everything to GitHub. I'll also upload Dropbox later today. But I think this is not a bad place to stop. So this is the final output, which I think, with a little bit more polish could be a publication figure. Does microbiota include viruses? It's a good question. I mean, it's a 16S. I think it's a 16S based database, so no. But I'm actually not 100% sure. I mean, so microbiota is not mine. I'm not. I mean, I know these people, but I think it's mostly 16S based. So I think the answer is no. But I think the answer is no. But yeah. Thank you. Yeah. Yeah. Right. Thank you, everyone. Yeah. And you can probably find my email if you have any further questions.